Hello. Last time we learned the basic idea of identification argument. And from this lecture and in the next chapter, we will study two important examples of identification failure. So when you learn the definition of identification, you may think it's obvious and like what is the problem with identification? Like we always identify whatever we want, but actually not. So learning identification failure examples will help you better understand why it's important to understand the identification. The first. So let's go back to the regression assumptions. There were four assumptions. Let me go here. So we had four, by the way, I updated the lecture notes, so a little bit different from what you got last time. These are four assumptions, and we did not use number four. So we needed three assumptions to identify the linear regression model. Of course, there are a few other implicit assumptions, but they are too basic, so we are not going to consider them as an assumption. Among these, linearity can be generalized to nonlinear cases later. So we are going to maintain assumption 1 for a while, just for simplicity. So extension of linearity, relaxing the linearity assumption is not difficult at all. So we are not going to consider it at this point, but we will look into the exogeneity assumption and the full rank assumption. So these two assumptions can fail. They can fail. So we will study what happens, what is the problem when either of them fails. So that's the main topic we will study from now on. So when the full rank assumption fails, that problem is referred to as the multi-collinearity. Multiple variables are correlated linearly. That's kind of the meaning of this term. And when the exogeneity assumption fails, then the problem is referred to as the endogeneity assumption. So a variable is endogenous, so the model has to explain that endogenous variable. This endogeneity problem is too important, so important that we are going to have a separate chapter, a whole chapter devoted to study the endogeneity problem in the following chapter. So the following chapter, the endogeneity, is studied separately in more depth. So today, in this lecture note, we are going to focus on the multicollinearity assumption, the problem. So I have read a few textbooks, and I find Stark and Watson, it's an introductory econometrics book, has a very nice chapter on this. So they have examples and nice intuition explanation. So I recommend if you have difficulties in understanding them. By the way, the reason why so typically when I learn econometrics as a college student or when I read textbooks, I find that most of them handle multicollinearity problem too technically. So it's an assumption about many textbooks consider the problem as a violation of the matrix algebra condition. So then there is no intuition behind it. So in this section today, in this lecture, I would like to connect as much as possible to intuition. I'd like to minimize the technical explanation, what happens in the matrix, why a matrix is not invariable, or blah blah blah. There are so they are important. These mathematical mathematical argument is important. You need to understand. You need to understand matrix algebra and like some basic concepts like rank, linear dependence, linear independence. But what's more important, I believe, is the intuition and how to utilize, how to understand the assumptions. So I'm going to focus more on the latter. So please understand it. First, let me state the mathematical definition, even though I think there are more important things to come. So the full rank condition fails definition. So it's when I'm defining the condition by its failing case if and only if the variables are linearly dependent. Then what is linear dependence? So this holds whenever they are not linearly dependent. Then when they are linearly dependent if you may write them in this way. If there are some weights, some combination of constants, so that, and if you calculate some kind of weighted average of those random variables, k different random variables or k number of independent variables, if you take weighted average, and if there exists some weight that makes the weighted average always equals to 0 with probability 100%, then something is wrong. So of course, we do not allow everything to be 0. So of course, one trivial solution is gamma 1 equals to 0, gamma 2 equals to 0, gamma k equals to 0. If every weight equals to 0, then this equality will be true trivially. So other than that case, if there exists a non-zero weight that makes the linear combination of those independent variables equals to 0, then you are in a problem. That implies that the full rank condition fails and the matrix is not invariable, or the matrix is non-singular. Matrix is singular. So when a matrix is not invariable, we say that the matrix is singular. I'm confused too. So this is a mathematical definition. So let's think about examples when this happens, when the variables become linearly dependent. The simplest possible example is to consider a dummy variable. Suppose that you define a dummy variable f, which takes 1 if an individual is female and takes 0 if not. And you define another dummy variable m, male, which takes 1 if male and which takes 0 if not. And think about, say, for example, y is wage. So wage is regressed on intercept and female dummy and male dummy and at a term. Assume that all the other assumptions are satisfied. Do you think it's possible? Can you estimate this? No. Your code, your program will result in an error. Will not run at all, because mathematically speaking, these two dummy variables are linearly independent, because always anyone is either male or female. So either m equals to 1 or f equals to 1. And when one equals to 1, automatically the other equals to 0. So sum without any weight, if you simply sum these two dummy variables, you will get 1. And by the way, then it is not 0. Then you may think, so in this case, you need to think that x1 is the intercept, right? And x2 is male, and x3 is female, male, female, anyhow. So then I will put -1, 1, 1. Then always you will get 0. Do you understand? So in this case, it is a multicollinearity for 3 variables. 3 variables, intercept, female, and male. So you cannot estimate that. It is not a matter of how many samples you have. Even if you have unlimited number of observations, you cannot estimate that equation. So when you run a program with this this regression equation, these days statistical softwares are smart, so they tell you your equation has a multicollinearity problem, so the program may automatically drop one of them. Say, since the solution is, there is no other solution, the only solution is to drop one. So remove m from the equation. That's the only solution. And for Stata, for example, Stata does do that, deletes one variable by itself automatically, recognizes the problem and take on action by itself. Anyhow, this is the simplest possible example of multicollinearity, and many students still face this problem. By the way, I didn't say this. One possible way is to drop male, for example, but alternatively, you may drop intercept. So the idea is, if you drop intercept, then by two variables, by these two guys, you cannot make their weighted average equal to 0, because always one of them is 1. So dropping intercept is another way to resolve this problem. And example 2. Now consider a similar regression equation like wage. Now wage is regressed on intercept, age, work experience. So work experience is how many years you have been in the labor market. So and education, how many years of education you got. This equation, this regression equation, has a multicollinearity problem, because think about this. Most of people enter school at age of 6. All right, first grade. Most of people become the first grader at 6, and most of people are employed, start their career right after graduation. So then this means your age, if you have lived like say 30 years, then the 30 years, among 30 years, the first 6 years, you were just a baby. And the following 16 years or so, the following 10-something years, you have been in school, and the remainder is your work experience, right? If you had no delay in education and getting a job. So this equation is true. Age equals to 6 plus experience plus education. So then you can show that so 1, 2, 3, 4 variables can be, if you combine them, let's put it this way. X1 is intercept, X2 is age, X3 is experience, X4 is education. What I do here is put 6 in front of the intercept. 6 is the weight, and the weight on age is -1, and experience and education get a weight of 1. Then 6 minus 1, 1, 1 weights will imply this equation. So will be 0. Therefore, they are linearly dependent. So in this case, you cannot include all these 3 variables at the same time. So you have to drop one of these 4 variables. This is another example of linear dependence and multicollinearity problem. So this is a simple introduction to mathematical definition of multicollinearity and full rank condition, linear dependence. So next time I'm going to focus more on intuitive explanation. So see you in the next video.